Now let's apply what we've done to adding the two expressions we have here, x over x squared minus x plus 6, x plus 3 over x minus 3. Okay, first we factor. The only thing we have to factor is the denominator of the first polynomial, or the first fraction in this case, and that denominator, as you can verify, factors at x minus 3 times x plus 2. Now, we need a common denominator for these fractions, and in this case it's very obvious. We have this denominator and this one. The x minus 3 is already here, so we just need an x plus 2, so our common denominator is going to be x minus 3 times x plus 2. However, we're going to go through the procedure, of finding that, or at least I'll point to it. And I'll say that the least common denominator is the least common multiple of all the denominators. So what we want to see is how our least common denominator, which you pretty much know to be x minus 3 times x plus 2, is a common multiple of this and this. Well, let's just talk about how we would build this up. The first thing we would need to build up our common denominator, just moving from this denominator to this one, we're going to need x minus 3. Well, there we have it. We're going to need x plus 2. There we have it. At this point, if we don't take anything away, this is going to be a multiple of this. Of course, the two are identical, so obviously it's a multiple. Now, we need an x minus 3, but we've already got it. So we don't need to do any more to get our least common multiple, or our least common denominator. Our least common denominator is the least common multiple of our denominators. Okay, well, now we know what the denominator is, so all we have to do is multiply this fraction by something divided by itself, as we saw earlier, and this fraction by something divided by itself. Well, in this fraction, we've already got the common denominator, our least common denominator, so we really don't have to multiply it by anything, but I'll just say, okay, we'll multiply that by 1, just so we can remind ourselves that we do have a step there, even by 1 over 1, if we'd rather do it that way. Okay, in the case of x plus 3 over x minus 3, we have to get denominator x minus 3 times x plus 2. Well, we've got x minus 3, but we're going to have an x plus 2. And if we're going to get one in the denominator, we're going to have to multiply by that same thing in the numerator. That's going to give us x plus 3 times x plus 2 in the numerator, and x minus 3 times x plus 2 in the denominator. Now, I'm running out of board space, so I went ahead and multiplied x plus 3 by x plus 2 to get x squared plus 5x plus 6, so that this fraction here is expressed as x squared plus 5x plus 6 over our common denominator. This one, of course, has always been over that common denominator. So now we can add the two numerators, and it would have been nice if I'd have done that correctly. Actually, I did. Okay, just thinking that was an x squared. So x added to x squared plus 5x plus 6. Well, we're going to have a 5x. We're going to have an x. Going to give us a 6x. And then we have the x squared and the 6, which are unchanged. And here's our result. And that's the process. It's exactly like the process we used earlier with some somewhat simpler fractions. But now we're going to be a little more formal, a little more meticulous about getting a least common multiple of our denominators and using that as our least common denominator. We'll look at one more example. As we have seen, the definition of average velocity gives us the relationship among v bar, delta s, and delta t in such a way that any two of these can be used to get the third. So delta s and delta t give us v bar and delta s can give us delta t, v bar and delta t can allow us to calculate delta s. If we know the values of two of the quantities here, we can find the third in a very straightforward way if we understand the definitions and have a little practice in applying them. Okay, the definition of average acceleration gives us a triangle that looks almost like this one, except that instead of v bar and delta s, we have a bar and delta v along with delta t. Again, I'm not going to go over how the definition of average acceleration relates to these three quantities. It's very straightforward, and you do need to be able to do that. Now, that's addressed elsewhere and in the videos and in class notes and in documents and so forth. Finally, you need to understand how the straight line v versus t graph and a straight line v versus t graph means that you have uniform acceleration in a way that I hope you understand. At least make sure you understand that uniform acceleration is the same as a straight line v versus t graph. In other words, in any case, the straight line v versus t graph, and which embodies uniform acceleration, gives you these relationships, okay, between v naught, vf, and average velocity, and that's the simplest of all the relationships, where the average velocity is just the average of the initial and final velocities, but also a relationship that can be easily confused because it's so easy to confuse average velocity, the symbol for average velocity, with the symbol for change in velocity. They look quite a bit different, but they are very easy to confuse at this point, and we've addressed that idea also. Okay, well, just by applying the definition of average velocity, definition of average acceleration, and this straight line graph, we get 7 quantities. Okay, there's 7 quantities in these pictures. First quantity we'll say is v naught, and it doesn't matter in what order these are listed, but I've listed v naught as the first, vf as the second, delta s, which you see here, as the third, delta t, which you see here and here, as the fourth. Acceleration. Now, if we have a straight line v versus t graph, average acceleration is the acceleration. So I don't have a bar over a here. I left it here because that is what comes out of the definition of average acceleration. If when we combine with a straight line v versus t graph, we can remove the bar because the slope of the straight line graph is always the same, and that's what represents the acceleration. It's unchanging. And then we have also delta v here, and I've got delta t also, and that's a mistake. That should be v bar, so I'm going to make that correction. So we have v bar, which appears here. So those are the 7 quantities that we get when we apply these definitions and the implications of the straight line v versus t graph. Those are the only quantities we need to reason out uniformly accelerated motion in most cases. Now, there are a couple of cases where we can't quite apply these triangles and get the reasoning, but we can apply them in a different way to get some equations that get us over that hump, and we'll talk about that later. Don't worry about that now. Okay, so any combination of 3 of these 5 quantities here can lead, just by pairing up quantities in ways that we'll see in a minute, to the values of all the others. Any 3 of these. We're not counting these among the, any 3 of these 5. We could throw these in, but then the idea wouldn't be as simple. And it's going to turn out that we just completely model uniformly accelerated motion. We can write equations that model uniformly accelerated motion in terms of these 5 quantities. And these 2 quantities are related when we try to understand what everything means. And they're related when we try to do the reasoning with these pictures. So let me write in a statement here. So I'm going to say that this pairing process, that I'll illustrate here in just a second, works whenever we're given this combination v naught vf delta s, or v naught vf delta t, or v naught vf a, or v naught vf, v naught delta s delta t, v naught delta t a, vf delta s delta t, vf delta t a, or delta s delta t a. It does not work if you're given v naught delta s and a. It does not work if you're given vf delta s and a. but we can derive equations to deal with these situations, but they don't fit into the scheme we're going to develop here. There is one other thing. It doesn't require a definition, so I didn't write it as one of these triangles, but it's worth noting. What does delta V mean? Delta means change in. What's the change in velocity? Now, change in velocity is final velocity minus initial velocity. So I'm going to write kind of a fourth sneaky little triangle here, but that triangle is completely unnecessary since we know what delta V means. We know what delta means, so we know what delta V means, and we don't need any definitions or straight line graphs or anything for that to be true. So there's no assumption behind that, but it's still worth writing down so that we have it for reference, so we don't, so that our pairing process can really be complete. I've written this kind of small over here. I say delta V equals VF minus V naught, which is true just because of the meaning of delta, so that we have a triangle, VF, V naught, delta T. It's delta V, not delta T. Let me fix it. Okay, it's VF, V naught, delta V. And we know that if we subtract V naught from VF, we get delta V, and it follows that if we add V naught and delta V, we get VF. If we subtract delta V from VF, we get V naught. Those are very straightforward relationships that don't require assumptions once more. Well, that's a picture of our situation. I'm going to go on in the subsequent video and use that picture. Let's apply the same procedure to this addition. We first factor our denominators. X squared plus x minus 12 factors into x plus 4 times x minus 3, x squared minus 9 into x plus 3, and x minus 3, and everything else, numerators are still the same. Our common denominator is what? Well, we need an x plus 4, we've got one. We need an x minus 3, we've got one. Here we need an x plus 3, we don't have one yet, so we better put one in there. And we need an x minus 3, but we've got that. Okay, so here's our common denominator. To put this first expression over that denominator, to get the expression in a form where it has the common denominator, we first observe that its denominator has everything except that x plus 3, so we multiply by x plus 3 over x plus 3. The second denominator is x minus 3 times x plus 3. We got that. But we don't have the x plus 4, so we'd better multiply by x plus 4 divided by x plus 4. That's going to match up our denominator. So our common denominator expressed here and expressed here is just the same as what we said it was. Our numerator here is going to have to be x plus 2 times x plus 3. And we're going to multiply that out to get x squared plus 5x plus 6. Our numerator on the second fraction is going to be x minus 1 times x plus 4. And we're going to multiply that out to get x squared plus 3x minus 4. And then we're going to add these two terms to get 2x squared. 5x and 3x is 8x. 6 and negative 4 is 2. So our final result is 2x squared plus 8x plus 2 divided by our common denominator.